This video will cover fractional exponents. As you remember, in the last video we talked about integral or integer exponents, and in this one we're going to talk about fractional exponents. And if you recall from previous courses, a fractional exponent means that you have a radical. You can kind of think about these two things as synonymous. So if you have, for instance, a square root, this would be the same thing as whatever that base is to the 1/2 power. And so this is what our kind of base definition is. However, whatever what they call an index is, so that would be your square root, cube root, fourth root, it would be that number on the root, that's your index, then you can rewrite that as your base to the 1/n power. Likewise, if we have, we can think about it this way, if we had a root to a power, well, we could rewrite that as a to the 1/n to the mth. And we know from our previous lesson that if we have a power to a power, then we can multiply these. So 1 over n times m would simply be m over n. And so that's how we can simplify and show that a to the m over n is either the nth root of a all to the m power, or you can put that m power attached to the a, and I'll put that under the root to the nth root. Definitions 12 and 13 are similar to what we talked about before. We can distribute an exponent over multiplication. So if you think about this as being ab to the 1/nth, then you can distribute this to be a to the 1/nth, b to the 1/nth, which is just the nth root of a times the nth root of b. And so this works likewise for division as long as we're not dividing by 0.
Now let's take a quick look at how those definitions work. So for instance, if we look at 3x squared times 3x squared, using the laws of exponents, we would have 3 to the 1/2 plus 1/2, which is 3 to the first, or 3. Likewise, if we look at the square root of 3 times the square root of 3, this is the square root of 3 squared, and again, our rules for radicals show us that if you take the square root of something and then square it, you get back to the original number. So we can see here how they have the exact same number. And we can see here how we've proven that the fractional exponent 1/2 is the same thing as the radical here, square root. Similarly, if we look at 5 to the 1/3 times 5 to the 1/3 times 5 to the 1/3, that's 5 to the 1/3 plus 1/3 plus 1/3, all in the exponent, which again, a third plus a third plus a third is 1, so we end up with 5. Similarly, when we have the cube root of 5 times the cube root of 5 times the cube root of 5, well, that's the cube root of 5 cubed, and again, the cube of a cube root gives you what's inside, which is 5. So again, we end up with the same thing here.
If we have, for instance, 7 to the 1/4 to the 4th, we say that we multiply those exponents. So this ends up being just 7 to the 1st. If we multiply that 1/4 times 4. And likewise, we know that the 4th root, the way to get rid of a 4th root, would be to raise it to the 4th power, and this also ends up being 7. Sometimes, if we want to simplify radicals, it's easier to write them with their fractional exponent. So if, for instance, we look at the radical form of this, 8 squared, and then the cube root of that divided by the cube root of just simply 8, we can rewrite it as the fractional exponent, which we'll see in a second. Or we could simplify and say, okay, well, we've got the cube root. Well, 8 squared is 64. And the cube root of 8, we know, is 2. And the cube root of 64 is 4. We divide that by the 2 that we found before, and we are left with 2. Sometimes it's easy like that. Sometimes it's not. So sometimes we like to rewrite this instead as the fractional exponent. In this case, we would have a to the 2/3 divided by a to the 1/3 if we change those radicals to fractional exponents. And in this case, we would have a to the 2/3 minus 1/3, which is just a to the 1/3. And if you wanted to rewrite that as radical form, it would be the cube root of 8. And we know that the cube root of 8 is 2. So either way, we end up with the same answer, which we should. It's just two different ways of looking at it. Something else to kind of keep in mind here when we evaluate radicals is that when we take the square root of negative numbers, this doesn't work out so well in the real numbers. It's fine in the complex numbers, which you talked about in Tech Math 2, but it's not going to work as much in the real numbers. So in this case, the square root of negative 9, if you wanted to, you could write that as imaginary number 3i. Or you could say that it's not real, but we can take the cube root of negative numbers. So the cube root of negative 27 is simply just negative 3, because if we multiply negative 3 by itself, and we have that base 3 times, then we end up with a negative number. So the cube root of negative 27 is negative 3. Now I want you to take a second, example 17, and evaluate both of these expressions. So for part A, there were two different ways that you could have done that. Either way, you should have ended up with 4. And for part B, then there's really only one way to look at this, is to look at it as the fraction. Then you can convert that to being a cube root, a fraction, and then you take the cube root and you end up with 1/2. I want you to pause the video again and try to simplify these next two examples. Remember that anytime you're adding or subtracting fractions, that you need to make sure you have a common denominator. So for this one, 2/3, you would have to convert that to 4/6 to make sure you have the common denominator. And so for part A, you should have ended up with x to the 1/6. And for part B, you should have ended up with x to the 3/2, because it would have been x to the 9/6. And we can reduce that fraction. Even though it's an exponent, we can still reduce it to x to the 3/2. If we wanted to rewrite either of these in radical notation, this would be the 6th root of x. And this here, we've got, again, options. This would either be the square root of x cubed or the square root of x quantity cubed. It's up to you which way you prefer to write it. A couple more examples. We can use, again, the laws of exponents. In this case, if we've got x to the negative 3/2 to the negative 2/3, we are just going to multiply these two exponents together. And one of the nice things about this is that they are reciprocals of one another. So 3/2 times 2/3 is simply just x to the first power, or x. We can also distribute an exponent if it's negative and radical, and negative and fractional. So if we distribute this exponent, we end up with a to the positive 30/3, b to the negative 45/3, and c to the positive 75/3. And we, again, want to reduce those fractions. There's no need to leave them in this form. 30 divided by 3 would give us simply 10, so that's a to the 10th. 45 divided by 3 would give us a b to the negative 15th. And 75 divided by 3 would give us a c to the 25th. Last thing we want to do is to make sure that we have the positive exponents. And so this is going to be a to the 10th, b to the 15th, over c to the 25th. A few more examples. Sometimes it's helpful to rewrite things as fractions if we need to. So in this case, we've got 4t to the 1/2, and we want to multiply that by 2t to the 1/2. And what we really need to rewrite is this last piece, plus 1 over, well, 2 to the first is just 2, and t to the 1/2 if we put it in the denominator. So now, when we multiply these together, we get 4t to the 1/2 times 2t to the 1/2. And when you distribute to the second one, you should get a plus 4t to the 1/2 times 1 over t to the 1/2. And now if you pay attention to how these simplify, 4 times 2 is 8. T to the 1/2 times t to the 1/2. What does that give you? Well, you would add those exponents because we're multiplying, so that means we add the exponents. 1/2 plus 1/2 is 1. What about over here? We've got 4t to the 1/2 times this fraction, 1 over 2t to the 1/2. If we rewrite this first one as being over 1, then it's a little bit easier to see as fractions. 4 divided by 2 is 2. T to the 1/2 divided by t to the 1/2 is simply just 1. So what we are left with is just 2 times 1 over 1, or 2. And so that's our final answer simplified there. A couple more examples just to make sure that we are practiced with everything. Again, remember what an exponent means. I do not want to see anybody trying to distribute this exponent because there is a plus symbol here. What this means is x to the 1/2 plus y to the 1/2 times x to the 1/2 plus y to the 1/2. If you try to distribute that exponent, you're going to lose a term and it's not going to be correct. So in this case, x to the 1/2 times x to the 1/2 is x to the 1, because 1/2 plus 1/2 is 1. When you multiply the two outer pieces, you end up with x to the 1/2, y to the 1/2. When you multiply the two inner pieces, you get y to the 1/2, x to the 1/2. And when you multiply the last, you end up with y to the 1/2 times y to the 1/2 is just y. So when we simplify here, we get x. These two middle terms are really just the same thing. They are just written in opposite order. And so we've got plus 2 of these, x to the 1/2, y to the 1/2. For some reason, I see a lot of people getting confused about what to do with the exponents here. Nothing has changed. When you're adding two things together, the only thing you can change is the coefficient. Exponents stay the same. They are not going to change. And then finally, we have y. Exponents only change for multiplication and division. So again, look through that one, make sure you're very comfortable with that because you are going to see that again in the homework and in Tech Math 4 and in Calc 1. So make sure you're very comfortable with what that means to square an expression. We've got two more examples here. So if we look at example 23 here, we want to make sure we simplify the inside first. We could distribute the radical, but it would look kind of messy taking the square root of 6 and square root of 8. None of these are perfect squares, so let's simplify the inside first. We end up with, if you want to simplify, 6 divided by 3 leaves you with a 2, and then you have a 2 times 8, which is 16, and then we can take the square root of 16, which is 4. Like I said, none of those were perfect squares to begin with, but since we simplified things, it ended up being a nice perfect square. I want you to pause the video for this last example, and all we're doing here is plugging in the values and evaluating the function using our laws of exponent. So for this last one, you should have been able to simplify to get 256, or you could just leave it as 4 to the 4th. Either one of those is acceptable. Again, all we did here was plug in the value 16 and 12. If we simplified here, 12 divided by 3 is 4. And the way that I wrote it was the square root of 16 times, or raised to the 3 is the square root of 16 cubed. And I do this because it's easier to take the square root of 16 and then cube it than it is to cube 16 and then take the square root of it. So we know that the square root of 16 is 4, like we saw up above. And so then we would cube that. So we can either rewrite this as 4 to the 1 times 4 cubed, which is 4 to the 4th, or we can simplify it to be 256. So this concludes the video for 8.2. Go online now and complete your homework. And when you're done, move on to the video for 8.6.